Greetings, my name is Stephenson-Moe, and today I'm going to be discussing how to detect attackers on your ICS network using your own measurements using a technique known as state estimation. A little bit about me. I have 8 years experience more or less in InfoSec. I started off my career with a power utility. It's a big one in the South. I'm educated as a mechanical engineer, but I've taught myself pretty much everything I know in InfoSec, and I currently work as a penetration tester for Coalfire Federal. A little bit of background on ICS attacks. So attacks on critical infrastructure are a thing now, as I'm sure everyone is aware. As control systems continue to adapt more common technology that are used in IT, they open themselves up for all the vulnerabilities that normal IT systems are prone to. The big difference is these systems are hooked up to massive machines and things that can kill people and cause major disruptions to society. So that's what we'll be talking about today. For the purposes of this talk, I'm going to be defining attacks into two types. One, hard and fast, which we will not really be discussing. Think DDoS, ransomware, things that are noisy, things that cause a lot of chaos suddenly and are very obvious. Instead, we're going to be talking about low and slow attacks. So think, Trojan, backdoors, anything Stuxnet, anything where the attacker is trying to be stealthy and remain undetected. So traditional intrusion detection, you've got your IDSs, your firewall, your antivirus, DDoS mitigation, that sort of thing. Those are all things that are used commonly in IT, but most utilities, in my experience, stop there pretty much. When it comes to a lot of these security products, their focus is on stopping them at the IT network before they can pivot onto the network, or just making it impossible to pivot onto the network by being disciplined about strict segmentation between the two networks so they can't get through. The shortcomings with these products and this approach is that it doesn't always work, as we all know. It doesn't really embrace a defense in depth strategy. Most technologies, and the problem with most of these technologies is OT technologies like RTUs, PLCs, ladder logic controllers, you're not able to put a lot of these technologies onto these networks. One reason is because they disrupt network performance. And most engineers won't let you put them on there because they'll mess with things like reliability, latencies, jitter on the network. And even if you could put them on, regulators like NERC will often certify systems together as a unit. And any kind of change, like adding a IDS or changing an antivirus signature, could cause your system to require being recertified. So is there an answer to this? Like, is there really any better way? Well, I think there is, and it's physics. So the basic idea behind it is that the laws of physics don't change, and neither do most ICS systems. They're pretty much static. They change very little over time. Power systems, once they're set up, the actual physics behind how they work changes very little, and often the systems themselves change very little, so it gives you, as a security professional, the opportunity to look more at a whitelisting model, which I know many people cringe when they hear that, but in this case it's kind of appropriate because a lot of these systems are very static. So state estimation you can think of as sort of a numerical whitelisting model. So a little bit of background on state estimation. It was a technique developed in the power industry originally around the 1960s. It was not developed for security because no one was thinking about that back then, but instead is more of a way of ensuring reliability on the grid and preventing future blackouts by detecting garbage data more quickly. But for given certain circumstances, it gives us the chance to look at it as a security technique. So the basic idea behind state estimation is you take raw measurements from your sensors. You have a state estimator that you run it through that gives you state variables, which the state variables feed into your physics model, which is similar to the state estimator, to give you measurements that you would have predicted. You then subtract those from the raw measurements that you got, and you plug the output into a chi-squared distribution function, which will give you a probability that your measurements are either garbage or being tampered with. So there's no way around it. This talk is very math heavy. I had to learn everything about InfoSec on my own, so, you know, InfoSec people can learn some math now. It's my chance for revenge. In more mathematical terms, we basically have a bunch of measurements which we give by the vector z, and we are trying to find state variables x that we can describe those z's in terms of. For this technique to work, because it is a numerical method, we need more z's than x's. If the sizes are equal or less than, then this doesn't work because our system is either fully constrained or under constrained, and we can't make a prediction on whether or not our data is good or bad. So to put that another way, we compute a system of functions, h of x, which is a whole bunch of functions that are comprised of our state variables that give us our measurements. So since this is, we have more measurements than we do variables, we have, you know, n plus m unknown equations, and m equations will have more equations than unknowns, which means that there are more than one solutions to this, which means this becomes an optimization problem. So for the purposes of this talk, we're going to use the least squares method. There are other ways of solving this as an optimization problem, but least squares is the most accurate. So our goal for least squares is to minimize j, which is nothing more than the sum of the squares of the differences between the expected measurement and the actual measurement. Oftentimes we'll put some kind of weight onto the measurements that's basically a description of how accurate it is. It's given by 1 over sigma squared, and sigma being the standard deviation of the measurement. So the way we minimize j is the way we minimize anything else, by setting the derivative with respect to the state variables equal to 0. Now, because we're taking a derivative, we'll also need the derivative of h, or the Jacobian, since it's a matrix, which we do nothing more by just taking the partial derivatives with respect to each of our x variables. Here. I'm not going to go through the entire derivation because for the purposes of time, but essentially what you end up with is an iterative method where you have an initial value that you guess subtracted by some delta, and that gives you a next value, x1, which you then feed back into your x0 value to repeat the algorithm over and over again until your residuals end up being next to 0. So once you figure out j, you then figure out the probability that the sum of the least squares accurately reflects the data you're getting. And this you get by putting in p for zeta, your probability for zeta, and your degrees of freedom here. So obviously the more degrees of freedom, as you can see by this, the cleaner an answer you'll get. As you can see, where you only have 1 degree of freedom, this doesn't really tell you a whole lot right here, whereas if you have 10, you get a much cleaner solution with your most likely case being either close to 0 or close to 1. So you take 1 minus that probability, which will give you your likelihood that the measurements have been tampered with. So a result of 1 means that your measurements are perfect, and 0 means that there's no way those measurements can be accurate. But obviously for this to work, we want lots of accurate measurements with low standard deviations. So some basics about power, because we're talking about this in the context of power, because it was invented for power systems. We primarily work in phasors. We don't really work very much in the time domain because it makes the math a whole lot easier. But otherwise, you'd have to work with complex sines and cosines and stuff like that, which is really messy. You can basically think of a phasor as a rotating vector that rotates counterclockwise and has a offset and a magnitude, essentially, from other vectors. So, as you can see, Drake says phasors don't work in the time domain because it makes your math a whole lot easier rather than having to figure out voltage drops across inductors and capacitors using a lot of complicated calculus. So that does have consequences, though, for our math. We can no longer use the simple equation power equals voltage times current. That does not work anymore. Instead, we have three concepts now. We have apparent power, real power, and imaginary power. So your real power, or your apparent power, is your voltage times the complex conjugate of the current, which is broken into two components: your real power, which is what you think of when you think of electricity, and your imaginary power, which can kind of be thought of as power that is basically being bounced back into the grid because of things like inductances and capacitances on your load. The Beer model is often used as a way of thinking about it, and optimizing this is a big part of being a transmission engineer. So some basics on how the grid works. Power plant makes the power, low voltage stepped up to high voltage, transmitted at high voltage to a transmission substation, to distribution substation, to small transformers on poles, to your house. So a potential attack that we would worry about, on a simplified grid like this is an attacker going after something like a numerical relay. So I'm not going to explain like how an attacker would do that, because we're all adults here, and thinking about malware on something like a numerical relay running Windows CE is not something too far-fetched. But essentially, for the purposes of this, we're worried about an attacker who's very subtly trying to change a setting in either the potential transformer or the current transformer, which would give a bad voltage or current reading. This could be bad because it could cause a relay to not break when the voltage conditions are dangerous, or it could cause it to break and cause disruptions when situations are not dangerous, neither of which is ideal. So we're going to see if we can use state estimation to detect this in a simple example. So this is about the simplest example I could come up with for state estimation. Normally a real-life state estimation would be way more complicated than this. But for this we have a generator and a bus and two readings on one relay, power, and then two readings on the other one for real and reactive power, and a voltage reading right here on a second bus, and a transmission line in between the two. For the purposes of making the math easier, we're going to assume that the power company is giving us the voltage here, so we don't need a sensor, and that the voltage is 1, and we know that for 100-degree certainty. This makes the math a bit easier. So we call this a virtual measurement, essentially. So we're not taking this measurement, it's just given to us. And these are the other measurements that our system is getting, and we want to know if these measurements are legitimate or if they've been hacked. So first, we need a set of equations to describe the physics behind this system. So we have our first Z, which is equal to just the voltage. So that's H1 equals V2. It's pretty simple. The others, we're taking the real part. So we have 4 power measurements. power 1, 2, real power 1, 2, real power 1, 2, reactive power 1, 2, real power 2, 1, reactive power 2, 1, which is simply nothing more than the formula we took earlier with real and imaginary components taken respectively. So just by using Ohm's law, we can get the current. We don't need to measure it directively, just by taking the differences between the two voltage phasors and multiplying by the impedance on the line. Through substitution, we get power 1 and 2, and then we take the real component of it to get the real power on the first line, and then the imaginary power on the bus 1. And then we can do the same thing to get power on real and imaginary power on bus 2. Now that we have our equations and we know V1 for a certainty, we can cancel it out, and that makes our equations form into this nice H matrix that looks like this. And now we have all of our equations in so we have now two unknowns and all our measurements in terms of that, which are delta 2, which is the phasor offset between voltage 1 and voltage 2. We can just call, since delta is just a offset, we can just arbitrarily call one of them 0, which again makes our math easier. So we only have two state variables that we need to know as opposed to 3. So now for optimization. So as we recall earlier, our goal is to minimize J, which is simply the H values minus the Z values squared and added together. So it expands out to this. Using substitution with H that we just got, it expands out to this. It's big, long, and nasty. So then, using the equation that we have, the algorithm that we came up with earlier for least squares, and using this weighted matrix, which is just nothing more than a whole bunch of weights in a diagonalized matrix to make the matrix multiplication easier, we get this for our H, for our Jacobian of our H equations. We now run the algorithm, and the nice thing about the least squares algorithm is it's auto-correcting. So you can start with any guess and it's going to lead you in the right direction. So we start with an initial guess of 0 for the angle and 1 for the voltage. We run it and we get our first iteration. We get this for x1 and this for our residuals. And while these residuals are low, we can probably do better. It's always a good idea when you have a nonlinear system to run the equation at least twice. So we run it again, and we get this for our x value. Sorry, we use this as our input for our x's, and we run the equation, we run the algorithm again, and we get this for our second iteration for our x values, and this for our residuals. This looks a lot nicer. So we then normalize these residuals by dividing by the standard deviation, and we get this. So then it's the sum of the squares, so we square all of our normalized residuals and get this. We add them all together, and we get J equals 20.76. So now we use that as input for our chi-squared matrix, using 20.76 as our input for the zeta, and our degrees of freedom as input for which line we should follow, and we get something that's up here. So for the amount of degrees of freedom, that's a pretty clean answer that our data is definitely being tampered with, and somebody is messing with one of the values that our relay is reading. Okay, well that's great, but now how do we discover who the culprit is? Well, it's actually pretty simple. We can determine which sensor was bad simply by throwing out measurements and seeing if that lowers our J. If it lowers our J, then it's likely that that measurement was the one that was messing us up. But as you can see by this chart, when you throw out measurements, you lose degrees of freedom. So now instead of operating on the 3 line, we're operating on the 2 line. So if you don't have lots of redundant measurements, this isn't, you won't get a clean answer often. So using the previous example, we start with measurements that we think might be bad, and there's really no way to do it than just guessing. So we start off with Z4, chuck that out, we get J equals 4.16, and our new probability that we get is 12.5 by plugging it back into the chi-squared equation. So it could be that one, kind of unlikely. So then instead we try chucking out Z5, and we get 18.21 for J, which corresponds to 0.01 from the chi-squared function. So it's probably not that. So then instead we try Z2, and we get 1.626 for our J, which gives us a 44.34% probability that the estimations now make sense. So as I said before, with 2 degrees of freedom, you often won't get a clean solution, but it's most likely that Z2 was the measurement that had been attacked or was being compromised, since this raises up the probability so dramatically. So this tells us that the attacker was most likely manipulating the reactive power reading on bus 1. So with higher redundancy, again, and cleaner data, we get a more definitive measurement answer on what the measurement is that is being attacked. So in summary, state estimation, step 1, create a mathematical model of the system you're trying to analyze the states of. Calculate the least squares estimates for the state you're trying to estimate based on the given measurements. Sum the squares to give you J. Calculate 1 minus the chi-squared test output, where V is your degrees of freedom, and look at the output and see if your measurements make sense. So benefits of state estimation are, 1, you're using measurements that you already have. That's probably the biggest one. So as far as defense in depth goes, this doesn't require doing any tricks to add, normal commercial off-the-shelf IT security technology onto an OT system, which is a big plus. And if you work in the power system industry, you already have these. ABB Spider, GE LoadFlow, Siemens Spectrum. There's lots of commercially available state estimators out there for the power industry that, again, were not designed for security, but could be potentially utilized for security. It makes life much more difficult for an attacker to be stealthy. If an attacker is attacking your sensors, they have to be, especially if you have lots of accurate redundant measurements, they need to be much more careful about how they manipulate those measurements to avoid detection. And a big one too is you can use it on legacy analog equipment by doing some digital conversion, but legacy or analog equipment, it's a technology that can be used on analog equipment. So future work, because this isn't really something that's being used right now for security anywhere that I've seen, and if somebody knows better, please correct me, is what would be the best way to build a state estimator? We have ones that are commercially available, but maybe it's a better idea to integrate the data we already have into a data solution, like Splunk or Elastic or some other SIM, or maybe it's better to build it onto Splunk, like a Splunk app or an Elastic Stack app or something like that. There's really no telling. The techniques it's purely a numerical technique, so it could be deployed a numerous amount of ways. There are lots of options, so it's be interesting to see what we discover. Can be used anywhere. Because it's a numerical technique. Any system that's roughly stable and follows the laws of physics, you can use state estimation as a technique for detecting an attacker. It's an ICS intrusion detection technique, not just useful for power industry. The only real limitations are that the system needs to be mostly static. Once things start changing over 10 hertz, there's research into dynamic state estimation, but it's by no means a well-established technique. So is state estimation a silver bullet? Of course not. We're all adults here. We know that there are no silver bullets. So it does have drawbacks. Requires a well-understood, documented physical model of the system. Lots of redundant measurements, and you're only able to determine if the data is actually garbage. So you're not actually able to determine if the data is malicious. Again, this is why it works best in industrial environments where you have knowledge that your sensors are to a certain degree reliable, because the manufacturer has told you that you have a mean time to failure or a certain standard deviation, and it is what it says it is, and not something else, because you need to be able to trust that your sensors work to a certain degree before using this technique. Additionally, integrating state estimation into security is pretty much non-existent at this point. Most SOC teams have no idea how most of the systems, like if they're defending physical systems, they often do not know the physics or how the actual physical system they're protecting works. And even if they did, there aren't any SIMs that have any ability to build state estimation into them easily. And the state estimators that do exist have no easy way of being integrated into security products. So, of course, the answer is teamwork. Engineers that understand state estimation and the physics behind what they're doing need to work with the blue teamers, right? Teamwork and leadership is the answer that fixes this problem, because often you'll have people that understand this stuff. They just need to work together, and by working together they'll make us all safer. So special thanks to Professor Sakis at Georgia Tech. I used some of his work in this presentation, and that's it. I hope you've enjoyed this presentation, and I hope you learned a lot.